this problem we're looking at a tank, and it's a tank holding 100 litres of water in which 20 kilos of sugar is dissolved. So these types of problems are just commonly known as tank problems. And usually you have a tank that has an input and an output. And the input can have a solvent, a solute like sugar or salt or something coming in, and then an amount of that solute going out, or it can have pure water going into the tank. They're two slightly different problems, but the way that we put them together is the same. So if we look at this one, we've got a tank that holds 100 litres of water. So first thing I'm going to do is just draw myself a picture, and I've got 100 litres of water in there, and it says here that initially we have 20 kilos of sugar dissolved in that 100 litres. So that means that when t equals 0, mass, and that's going to be in m, mass of kilos of sugar is 20. So as soon as I've used something, I'm going to tick it so I don't need to worry about it again. We've got water running into the tank at a rate of 1 litre per minute, and the solution is stirred, and some of that solution is then pumped out at 1 litre per minute the other side. Okay. Now the first thing with a problem like this is to determine whether or not the volume of the tank is changing. So the volume of the tank here, we have to think about what's coming in and what's going out. And you can see that we've got 1 litre going in, but then also 1 litre going out. So that means that the volume of this tank doesn't change. Okay. If we had different rates going in and out, so let's say, for example, this is not the same problem, but let's say that you had 1 litre per minute going in and 2 litres per minute going out, your volume would be changing, and your volume would be 100 litres, what we started with, and then for every minute, in a situation like this, every minute you lose 1 litre, because you've got 1 litre coming in but then 2 going out. So for every minute you lose 1 litre, so that would be written as minus t, because when t equals 1, you lose 1 litre. When t equals 2, which is time in minutes, you lose 2 litres, and so on. So the volume would be actually, it would involve a variable, t. In this case, our volume doesn't change, so our volume is just going to be 100. It doesn't have any t involved. Okay. Now the other thing we need to do is think about the units we're interested in here, and you can see that in part D we're looking at m against t. We want to look at a differential equation relating m and t, so that would mean we're looking for dm dt, and that means that all of our rates have to be kilos per minute, because we've got m and t. So if we look here first of all at the rate going in, this rate here is a vt rate. So this is like a dv dt going in. This isn't really what we want kilos per minute. So what we also have to think here, and I'll do this in red, is how much sugar there is at each of these different steps. Now first thing is we know that water is running into the tank, so that means that we have no sugar coming in per minute. Okay, so that tells us what's coming in. At any time t, we have m kilos of sugar in solution, and the reason we use a variable here is because this is changing. Okay, so as water's going in and coming and solution's coming out, this amount of sugar in here is changing. Starts at 20 and then it will reduce because you're not adding any more sugar. Now what's coming out here, we have to think about the amount of sugar that's coming out at any particular time. Now I've got 1 litre per minute coming out. What we need to know is what constitutes 1 litre of solution. And in 1 litre of solution, we can think about having m kilos of sugar over 100, and that's going to be our concentration. So our concentration of sugar is m kilos per litre. Okay, now remember we want kilos per minute, so what we can do now is put these two things together. We've got 1 litre per minute coming out. In each of those litres we have m kilos per 100 litres. That's the concentration of sugar. And so that means that we have 1 times m, which is m kilos, and 100 on the bottom. And the cool thing that you'll see happen, 100, go away, 100 minutes. The cool thing that you will see happen is that the litres cancel on the top and bottom. So it gives us the proper units that we want, kilos per minute. So we've got m kilos per 100 minutes as our rate, m over 100 kilos per minute. So what I'm going to do now is I'm going to highlight two important things. That with a differential equation, so differential equations for tank problems have a particular setup to them. They're always written, and I'll just get rid of this section here. They're always written as your rate that you're interested in equals your in rate minus your out rate. So for the question that we're interested in here, we're going to be looking at dm dt. Okay, so the first part here, part A, is at what rate is the sugar being removed at time t minutes? And you can see here that the rate the sugar is being removed is m over 100 kilos per minute. Kilos per minute. Okay, so m over 100. So that's A. B asks us to set up the equation. This is where we're going to use this, and I'll put this in a box because it's really important. Let's use this expression. So the rate we're interested in is the rate of change of the amount of sugar per time, per minute, dm dt. The in amount. I've written this in red, so you can see we've got no sugar coming into the system. So there actually is zero sugar coming in, 0 kilos per minute. And then we did our work here to figure out the concentration, which was kilos per litre, times litres per minute, and we had m over 100 kilos per minute. So that's going to be our out rate. Okay, so we could just simplify that and write that as dm dt equals negative m on 100. So that would be our differential equation. So we've done that one. The next step is to solve the differential equation. And to solve, what we're going to do is going to separate the parts here. So I'm going to take the m over underneath. So all I've done is taken the m under and left a 1 in its place. And I'm going to bring the dt up to this side. So we have this expression. Equation, and now we'll solve it. So I'll just take this onto the next side. Oops. Drag that up. So we can integrate both sides. So we've got, I'm just separating the m underneath out as a 1 on m, and this is our other side. So we're going to have a log of m here. And this constant is going to become a coefficient of t, and we'll add another constant of integration. Now we know that m is an amount of sugar, so because m is always going to be bigger than 0, we can make that just a positive. We can get rid of the modulus signs, and I'm just going to write that as t on 100. Okay. Now what we can do is use our initial condition. And remember that the question told us that when t equals 0, or at the start, we had 20 kilos of sugar in the system. So that means that we have log of 20 equals 0 plus c. So that means that c equals log 20. So that gives us our c. So now we can actually solve this. We've got log m minus t, equals minus t on 100 plus log 20. Now we always solve for whatever's on the top of our differential equation. So it's dm dt, so let's solve for m. Okay, so I'm going to solve for m so that we have, I guess I'll do it, e to the log m. So I've taken the exponential of the left side, and I'm also going to take the exponential of the right side, so e to each side. Cool thing here is the e and the log cancel, so you get m equals. Here, e to the negative t on 100 plus e to the log 20 can be expanded. So it actually will end up being e to the negative t on 100 times e to the log 20. And the cool thing then that happens is the e and the log cancel. So we end up with m equals 20 times e to the negative t on 100, which is beautiful. So that's going to be our solution. Here's our particular solution. Now the last part of this question was to sketch the graph of m against t. So if we have a look at that equation for m, I'm just going to do a very rough little graph. Oops. So we've got t would be our independent variable, m is our dependent variable. We know that at the beginning of this process, we started with 20 kilos of sugar. Now the thing to look at is in an equation like this, and I'll just do this in red over here in a box. We've got 20 e to the negative t on 100, which is really the same as 20 over e to the t over 100, because the negative means that it's divided. Okay, what I want to think about here is what happens as t goes to infinity, so as t goes this way. Okay, what you're going to be doing is taking 20 and dividing by e to the infinity, which is a fairly extremely big quantity. So basically, as t approaches infinity, your mass of sugar approaches 20 over a really big number, so your mass would actually approach 0. So you have asymptotic behavior going on, and so your graph would look like this. Okay, so your graph might be a little bit more curved if you want to show. I'll just do that a bit more curved, like that. So your graph is going to be starting at 20, and then as fresh water is coming into the tank and diluting what's in the tank, the solution that comes out is going to be less and less and less full of sugar. And so you can see it decreasing, but it's extremely difficult to get all the sugar out of this tank. You'd have to leave that system running for a very, 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 very long time. Okay, so that's the idea with these types of equations, is really setting up your problem by using a diagram. If you use a diagram, you'll be able to tell what you have, what everything is in terms of units, and then also what units you need. So always consider the rate that you're interested in. Here it was dm/dt, which meant that I needed all my rates to be in kilos per minute. When they were given in litres per minute, I had to work with the concentration of what was in the tank. Okay, and then the basic differential equation for any tank problem is the rate in minus the rate out, and putting together your differential equation and then solving it by separating out the m's and t's, integrating, using your initial condition, simplifying, and then for the graph, considering the behaviour as t approaches infinity, because we're interested in positive time.